Hello everyone, Mr. Waz here, and welcome to WasleyScience. Today we are discussing water chemistry. So we are going to discuss why water is such a unique compound on Earth, and also discuss its three phases of matter, being a solid, liquid, and gas. Alright, so let's get started. What I'd like you to do to start is to number your page 1 through 9, and I'd like you to write down these questions and then to your best ability answer these questions. These are all things that were introduced to you in material that you worked with in 7th and 8th grade. So I'd like to see how much of it that you still have in your brain at this point in 9th grade. And the next 9 slides are going to be discussing this material. Especially leave a lot of space for number 9. Once you answer these questions, leave more space because the next following material is going to be about these questions. So it's a good way for you to test yourself how well you already know. So go ahead and press pause now. So the first question was probably the easiest, and the three states of matter are solid, liquid, and gas. Water is so unique than other molecules and other compounds because water is the only molecule that can exist as a solid, liquid, or gas naturally on this earth. Everything else really can't. It only exists as one state of matter. So if you take a look at this, you can see that water boils at 100 degrees. You can see that on the top here, that water boils at 100 degrees. In other words, it becomes a gas at 100 degrees Celsius, and it freezes at 0 degrees Celsius. If you look at all these other things, you can see they're just really ridiculous temperatures that would require them to either be boiling or freezing, so they would just have to stay in their state that we're familiar with. So oxygen becomes, it boils at negative 183 degrees. So for oxygen to go back to being a liquid, to be like liquid oxygen, it would have to be negative 183 degrees Celsius. So that's not going to really happen here on Earth. So you only see oxygen ever as a gas. And for oxygen to be a solid, yes, it could be a solid, but the temperature would have to be a negative 218 degrees. Same goes with carbon dioxide. It would have to be negative 57 degrees. However, we can condense carbon dioxide enough for it to be in a canister, which we use in a fire extinguisher. And then we have other things. So oxygen and carbon dioxide exist naturally as a gas. But copper exists as a solid because for copper to be a liquid, it would have to be some sort of temperature above 1085 degrees Celsius. So that's just not going to happen. And yes, you could have copper as a gas, but it would have to be 2562 degrees. That's not going to happen. Something interesting is that ethanol or alcohol boils at 78 degrees, whereas water boils at 100 degrees. That's why alcohol evaporates so much quicker than water. And you can see that titanium takes such a high temperature for it to become a liquid, which is why we use it for very durable needed things. And seawater actually freezes at a slightly lower temperature than water, which is why we often see the ocean or areas near the coast don't really freeze too often, because it takes even more temperature for water to freeze. And then mercury, as you know, exists naturally on this planet as a liquid. And the reason why we don't really see it as a solid is because it would have to be negative 38.8 degrees Celsius for it to be a solid. All right, so this question you may have gotten one part right and maybe not the other. What kind of bond is a water molecule? So water is a polar covalent bond. And first we're going to talk about what it means to be polar and nonpolar. A polar bond is when electrons are not evenly shared. So you'll notice on all water molecules that the two hydrogen atoms are like on top, and they're not really symmetrical. They're not like evenly spread out, and they kind of look like Mickey Mouse. And this is because that oxygen has a higher electronegativity than hydrogen. So the bottom of the oxygen molecule atom right here is very negatively charged, and the top is very positively charged. The two hydrogen atoms are the positive charge. And when you have a nonpolar bond, that's when the atoms are evenly spread out. So if you look at this CO2, you can see here's an oxygen, here's an oxygen, and then the carbon is in the middle, and it's sort of spread out. And you notice how you don't see that with a water molecule. So when electrons are not evenly shared and it's not perfectly symmetrical, this is a polar bond. It's nonpolar when it is evenly spread, like in this CO2. There are two types of ways that elements can bond. The first way I'm going to talk about is through an ionic bond. And this is when a metal bonds with a nonmetal. So my next slide is a periodic table, so I'll be able to show you what metals are and nonmetals are. But this often forms some sort of salt that can dissolve in water. An example is sodium chloride, which is table salt on your table. And what happens is that the metal will give an electron and the nonmetal will take the electron, and the positive and negative charge ends up holding them together. So the sodium gives an electron to the chlorine and makes sodium chlorine. Covalent bonds are when nonmetals bond with nonmetals, and this is what a lot of organic chemistry is about. Many important molecules in life are covalent bonds. And what happens instead of giving and taking electrons is that the nonmetals will share electrons with each other. And this sharing of electron pulls them together. So some examples of that is H2O, which is of course water, which is what we're talking about, CO2, carbon dioxide, and CH4, which is methane. So let's take a look at this periodic table here, and you can see what's labeled green are all of our nonmetals. But these nonmetals all the way to the right are actually known as noble gases, and they won't bond with anything. What you really want to pay attention to is this hydrogen in the top left, and the carbon, nitrogen, oxygen. Those are our four building blocks of life. So whenever those four elements there bond with each other, they often form many different types of compounds. Those are the covalent bonds that we're talking about. And with ionic bonds, when you have something in our first or second group here bond with something on the other side of the periodic table with one of the nonmetals, you have yourself an ionic bond. All right, so the ultimate question, why does ice float? Because what's weird is when something is a solid, the molecules should be becoming more condensed, which would cause them to sink in the liquid state of the same compound. But that doesn't happen with water. When water becomes ice, it floats to the top, which means that its solid state must be less dense than its liquid state. That's a very, very odd thing. And water is the only thing that does this in the whole universe. So why does it do it? It does it because when water becomes a solid, it forms this hexagonal sort of pattern, kind of like a beehive. And you can see that on the diagram on the left. It shows that the water arranges itself in these fixed positions. And when this happens, you can see the white in the middle there. That's empty space. So that's air right there. That's not water right there. So those pores, and you can't see them, they're not possible for you to see, but those spaces, when it all adds up together, ends up being more of a volume than when it is in a liquid state. So check out this diagram to the right. It shows when water is in a liquid state, you can see how it's all crammed together, but all the way to the right, you can see when it's in a solid state, it forms that hexagonal shape, which causes it to have a larger volume and thus be less dense. So again, water is the only compound that is known to do this when it is less dense in its solid state than in its liquid state. So now we're going to talk about surface tension, and this is why some things that may not be less dense than water actually float on top. So the key word here is that water is cohesive, meaning that water can stick to each other. Water molecules like to stick to other water molecules. And as I said before, water is a polar bond, a polar covalent bond. It's also known as a hydrogen bond because the hydrogen molecules stick to one another, making it very cohesive. And this creates surface tension, which allows some things to be able to walk on water. Just like this lizard here, if you go down here and click on this link, you can see this lizard run across the water. We can even balance a needle on top of water. Water is also very adhesive, meaning that water likes to stick to other types of molecules, such as a penny. So you probably did the penny drop lab in 7th grade, which is when you drop, using an eyedropper, you drop water onto a penny one at a time to see how many drops of water. And I'm sure you were surprised to see the amount of drops of water that a penny could hold. And this is because water is very cohesive, meaning it likes to stick to each other, but water also likes to stick to the penny. All right, now we're on number 8, which is what is viscosity? And you might need to practice that word a little bit. Viscosity is a liquid's resistance to flow. So a liquid with a high viscosity would flow slowly, and a liquid with a low viscosity would flow fast. So water has a low viscosity, and honey has a high viscosity. So I really like this diagram here because it shows the different viscosities of certain materials that you are familiar with. So what they did was they take a spoon of these materials and they just kind of tilt the spoon towards the ground and let the liquid roll off of the spoon and see what distance it takes before the liquid kind of breaks off and then begins to drip to the ground. You can see that water is all the way to the left because water has a very low viscosity. So when you tilt water with a spoon towards the ground, it will pretty much all roll off the spoon and then go to the ground. But milk is more cohesive, so it sticks to each other better. Oil is even more cohesive. Light syrup and then heavy syrup, and then you have chocolate syrup all the way to the right, is the most cohesive of these materials, which would mean that chocolate syrup sticks to one another the best and that it has the highest viscosity. So I really think this diagram is pretty interesting. So please take a little while to look at it and familiarize yourself with viscosity. All right, that was a lot of material right there. If you feel like you need a review, go ahead and use this link. Now I realize you can't click on this link from the YouTube video, so you will see this link down on the description on the YouTube video. I also will have it available on my website. Now we are on number 9. The last question, what is happening when water changes its state of matter? This will take a few slides. State changes require a gain or loss in thermal energy. And there is one of the most important tables, probably the most important table you will see for this unit. It has what happens when you go from a solid to liquid, liquid to solid, liquid to gas, gas to liquid, solid to gas, and gas to solid. It has what those are called, and it shows you when the heat is absorbed or released, and even gives you examples. Let's take a look at this first one here. Solid to liquid, all right, that's when melting occurs, so like a melting snowman or ice cubes melting. What is happening there is that heat is being absorbed. The ice cube is absorbing the heat, which is causing it to melt. Now when freezing occurs, heat is being released from the ice cube. Another thing to note is that when melting occurs and heat is being absorbed, that is an endothermic reaction, whereas when heat is being released, that is an exothermic reaction. And that is something that is discussed in 8th grade, so those shouldn't be totally unfamiliar words for you. When a liquid goes to a gas, that is also when heat is absorbed in endothermic reaction. That's called vaporization. Or when you think about the water cycle, that's called evaporation, and that's when water's boiling. And when it goes back from a gas to a liquid, we call that condensation. When water molecules are in the sky, in the atmosphere, and they condensate on particles of dust and form clouds, that is condensation right there. and heat is being released. And then you got your two oddball ones, a solid to gas sublimation and your gas to solid deposition. And this is when the liquid state is skipped. So instead of going from a solid to a liquid, sublimation is when it goes from a solid straight up to a gas. And a lot of heat is required to be absorbed for that. And then a gas is solid, a lot of heat is required to be lost for that to happen. It has to be a very quick drop in temperature. What's going to happen now is the following slides I'm going to very, very quickly show you. You can pause the video and take notes on these things, but they're very, very basic things. They're actually slides that I used to do when I taught 8th grade. You may have seen these slides before. You can use them as a review. If it's showing you material that you're not familiar with, then I recommend you definitely write this stuff down. It's very simple stuff. It shouldn't take you very long. Here we go. Particles in a solid are packed very closely together. Particles in a solid move by vibration. They only vibrate in place. They don't move around. They just sit there vibrating. Liquids have definite volume, but they don't have definite shape. Gases have no definite volume or shape. The change in a state from a solid to a liquid, we call that melting. What happens when a solid substance is at its melting point? This is actually really important, guys. The particles of the solid are vibrating so fast that they break free from their fixed positions. That's a very important one there, that they vibrate so fast that they break free from their positions. The change in the state from a liquid to a solid, we call that freezing. So going from liquid to solid is freezing. What happens when a solid substance is at its freezing point? Well, the particles of the liquid are moving so slowly that they begin to form in their regular fixed patterns and then do nothing but vibrate after that. The freezing point and melting point of water is 0 degrees. And the change from a liquid to a gas is called vaporization or evaporation. Well, we have evaporation here, which is a type of vaporization. Vaporization that takes place only at the surface itself. So when a puddle begins to shrink, that is an example of vaporization. Boiling is a type of vaporization. It's when a liquid changes to a gas at the surface and below the surface. So you'll see the gas bubbles come up and if you are boiling water, so those gases move up and then out. Condensation is the change from a gas to a liquid. So as I was saying before, when water evaporates into the air and then condensates on particles of dust, that's what forms clouds in the air. Condensation occurs when particles in a gas lose enough thermal energy to form liquid. And sublimation takes place when the surface particles of a solid gain enough energy to form a gas. An example of this is dry ice. And also you may have seen a situation when it snowed one day and you saw like gas, like steam above the snow. So that's a situation when maybe it got really hot in the middle of the day and the snow went through sublimation and just skipped the liquid state. All right, now your challenge is take a look at this graph. I hope you've seen this graph before. You most likely have. This is a phase change graph, and there are some temperatures that are missing on this graph that I would like you to draw this graph and then label properly. You should be able to guess at what temperature these flat parts are, and you should know what temperature is over here and over here and over here as well. Now my question is, why does the temperature stop increasing at certain points? Why do you see a flat part here and a flat part here when you see water going from an ice to a liquid and then a liquid to a gas? What is going on at this point with water? Great job, Roxy. All right, this slide is extremely important. I can't emphasize that enough. The flat places in the curve of the graph I just showed you represent when heat is being absorbed to change the state of matter of the water, but not enough heat is being absorbed to actually change the temperature. So time is still passing, because you saw on the x-axis it was time. Time is still passing, but the heat, instead of going towards changing and increasing the temperature, it's going towards changing the liquid from one state to another state. And this is called the latent heat stage. And that is when the phases are changing. So in other words, the first flat curve that you saw, which is right here, the heat is going towards melting the ice rather than increasing the temperature. So time is still passing and you see no temperature change. And this can happen for a minute or so, depending on the amount of water. The heat is going towards changing it from a solid to a liquid. And then up here you can see that the heat is going towards changing the water from a liquid to a gas. And one thing you should quickly notice is that the second flat line is a lot longer than the first flat line. That's because boiling water takes a lot more energy, or heat, thermal energy. It takes around 540 calories for water to boil, but it only takes about 80 calories for water to melt. Alright guys, that's all I have for you today. I have some links that you cannot click on from this YouTube video, but if you go to the description on the bottom of this video, you can get to these links, and they show you how the movement of solids and liquids work, as well as melting points. And if you click on the bottom videos here, you can see the first two are from our good friends the slow-mo guys, which in the first he pops a balloon, and in the second he drops a water. And what's really great about this is you can see adhesion, cohesion, as well as surface tension. The one all the way to the right shows crazy Russian hacker playing with some dry ice, frozen carbon dioxide. So he's doing all those things that you wish of doing with dry ice. Please feel free to click on the top right corner to subscribe to WasleyScience. Alright guys, thanks a lot and take care.